I think the craziest thing I have ever heard of is invisibility clocks, things which you can't see. And what that means is that as opposed to normal objects which reflect the light and you could see them, that's the reason why we see objects, these invisibility clocks don't reflect the light. When the light hits these objects, it goes around them and continues its way, which means that you can't see them. That was the beginning of what back then and still is called metamaterials. Materials which are not really possible today, or they were not possible yesterday, but they are becoming possible. That means that you have very special properties, optical properties. You can't see these objects. Now, if you can make optical properties which usually don't exist, maybe you could also make mechanical properties which don't exist, and that would give you mechanical metamaterials. Or you could make acoustic materials, materials with acoustic properties which don't necessarily exist before you made them, and that would give you acoustic metamaterials. Or maybe you could make materials for healthcare, for biomedical applications with properties that don't exist, at least not until you make them, and that is what I will call meta-biomaterials. So what I want to talk about today is meta-biomaterials, materials with impossible properties. And I like these properties and these materials because I would like to help patients with difficult skeletal diseases. So not routine skeletal diseases, but diseases which are very difficult to treat, like this bone tumor here. These patients usually suffer from two problems. First of all, when you give them an implant, the implant will not stay in the body for a long time because the bone metabolism is compromised, which means that the bone growth and implant stability is compromised. Secondly, they have usually a weak immune system. Many of these cancer patients have been undergoing chemotherapy, radiotherapy, which means that they have a compromised immune system, and that increases the chance of infection. So we would like to make or use these impossible properties of the materials to minimize the risk of infection and maximize the time that the implants could serve in the body of these patients. So implant longevity. Now, you can do these two things from many different viewpoints. You can create new drugs. You can't use new imaging technologies, but I'm an engineer. And in my native language, Persian, an engineer literally means somebody who is practicing geometry. So what I do is that I practice geometry. And with geometry, I create impossible properties. You could create impossible properties through geometry at least three different scales. At the scale of shape, or the macro scale, at the scale of microstructures, and at the scale of nanopatterns. So what I want to do today is to go through every one of these scales with you. Now, if you want to make this, you need 3D printing. This is an example of a 3D printing that we have here, 3D printing machine. There is a metal powder layer, and there is a laser which is coming on top of this metal powder and melting the areas that need to be melted, which means that you could make one layer. If you keep doing that, you could make anything you want, any geometry that you want. Now, if you do that, what you could also do is to create new implants. This is a tubular defect implant for the hip and the bone, which is also designed and 3D printed based on the images of the patient. So you could give this to the surgeon before the surgery so that the surgeon, he or she, could practice this operation before going to the operation theater. If you could do that for acetabular defects, you could also do it for hip implants, for the hip stems. Or you could do them for orbital floor fractures. These are all patient-specific implants, which means that they are designed for specific patients based on the images that are obtained from the same patients and 3D printed using the facilities that we have here at TU Delft. Now, is that all you could do? No, you could do more. What you could also do is to make implants which we call deployable implants. These implants are initially very small. That means that you could bring them to the surgical site with minimum invasiveness. Once they are at their position, you could deploy them so that they become large and load-bearing. So this is a demonstration of how it could work, is that, as you can see at the beginning, it could go through the jar, but once it's there, we deploy it, and you cannot get it out. And if you want to see how it works, it would be best to look at this video. So we have these multi-stable or bistable pieces which have two stable states. You could bring them from one stable state to the other and assemble them in an implant, which is initially very small, and if you activate these to go to the other position, becomes much larger. Now, that means that you could bring this implant to the surgical site, let's say a fractured spine, put it there in a small scale, then you could, for example, put a balloon there, inflate the balloon, which would mean that it goes from this stable state to the other stable state, and that allows you to have a reconstruction of the fractured spine. So there is a lot that you could do with the geometry at a larger scale, the macro scale, the shape, the mere shape of the implant, and the possibility to create very complex shapes gives you a lot of opportunities. But that's not all. You could also look at the microarchitecture and get impossible properties. Now, if you look at these porous biomaterials, these are very important because you could achieve at least 4 things with these porous biomaterials that are 3D printed. These are actually what you saw before and were being printed. First of all, they have mechanical properties which are completely similar to bone. So they are mimicking the mechanical properties of the bone. And you could do anything. You could get mechanical properties which are below bone or above bone or very similar to bone. And that means that the implants will not be unloading the bones. If you unload the bone, you will lose it. The bone is either you use it or you lose it. So if you want to not lose your bone, you have to load it, and that means that your implants should have properties which are similar to bone. Secondly, you can adjust the mass transport properties, how water, oxygen goes through these structures. If you want to make bone, you have to enable cells to get oxygen and nutrients, and that's only possible if you have specific properties that allow that to happen. Thirdly, the surface area, particularly the internal surface areas of these structures, are huge, thousands of times, sometimes larger than the corresponding solid elements, which means that you could put, for example, antibacterial coatings that kill bacteria. And finally, there is a lot of pore space that you could use to have drug delivery vehicles. So one of the nice examples that you can see here is a good example of how you could use geometry. These 3 polyperiodic minimal surfaces have a difficult name, but what it means to have a minimal surface is a little bit similar to a soap bubble. If you have ever played with soap bubbles, you know that they are minimizing their surface. That is what a minimal surface means, a surface that is minimizing the tension or the energy. And that would also mean that you have a surface curvature, which is the mean surface curvature, which is close to 0. So every time you have a concave surface, there is also a convex surface, and on average, they have a mean surface curvature of 0. Why is it important? It turns out that trabecular bone is also having a mean surface curvature which is close to 0. And what is also important is that the curvature is extremely important for bone tissue regeneration. So by using these little guys, which are accidentally also looking very beautiful, you could replicate the properties of bone from the geometrical viewpoint. Now, from the mechanical viewpoint, they are also very much similar to the mechanical properties of these guys are these bright green is what the materials that we make. And their properties are similar to the properties of bone. The spongy bone is this color, the red color is the cortical or compact bone, and you see that they have properties which are very similar to bone. Mechanical properties, mass transport properties, they could tolerate a lot of loading cycles, millions of loading cycles, and not fracture. And that's only possible because of this specific and beautiful geometry. Now, if you think about things which are impossible, one of the most important things which are impossible are negative Poisson's ratio. Now, that sounds a bit complex, but actually is quite simple. If you think about most materials, when you stretch them, they become thinner. That is what it means to have a positive Poisson's ratio. Almost all the materials, when you stretch them, they become thinner. There are very few, almost no materials which would become thicker. It turns out that if you use this bow tie shape to make porous materials, they become thicker when you stretch them. And that is a negative Poisson's ratio, a property which almost never happens in nature. Now, the other one is a honeycomb-like structure. This one has a positive Poisson's ratio. So why is it important to have negative or positive Poisson's ratios? Most implants in the hip region, similar to these, are loaded under bending, which means that one side of these implants are under compression and one side is under tension. The side which is under compression is okay in most usual materials because it is pushing against bone. And that's good because you will have more bone when you push against it. Moreover, you will not have the little particles coming off the joint that are getting in the space of the bone. Now, the other side, however, is not good. It's under tension. The material wants to become thinner, which means that it's going away from bone. The only way to have materials which are pushing against bone on both sides is to combine these bow ties with these honeycombs. And that never happens in nature. The only way to do that would be to make these a specific design and 3D print them. So let's see how it works.
The Reentrant hexagonal honeycomb is well known for its negative Poisson's ratio and can in this case be used to design an auxetic meta-biomaterial. This structure can be very useful in the field of orthopedics when combined with a conventional meta-biomaterial with a positive Poisson's ratio. Conventional hip implants may fail through wear particle-induced osteolysis. Articulation of the joint causes wear of the acetabular cup. The resulting polymer particles travel through the joint space and may lodge in between the bone and the implant, finally leading to inflammatory bone loss. Once the bone is gone, the implant's fixation may become inadequate. The aforementioned hybrid combination of a conventional and an auxetic meta-biomaterial may be the solution. Loading of this new meta-implant will in this case compress the conventional meta-biomaterial and stretch the auxetic meta-biomaterial, which will result in compression of the surrounding bone along both of the implant's contact lines. This does not only prevent wear particles from entering the bone implant interface space, it also stimulates bone growth and decreases the chance of bone implant interface failure according to Hoffman's criterion.
Now, this was one of the examples of impossible materials. There is simply no material which has half positive, half negative Poisson's ratio. But that's not the only example. The other example I have here for you are these guys. They are called Pentamode mechanical metamaterials, And what it actually means, this complex name, what it means is that they have a funny shape. If you look at them, they have this double cone shape. This is one cone, the other one is this one, and they are attached from the base. Now, because of this specific geometry, they could give you, first of all, any mechanical properties that you want. Any mechanical properties that are theoretically possible could be obtained by these materials. This was already discovered in 1995, 1996, but there was no way to make these materials. So it was only after invention of 3D printing that we could make these materials. Secondly, as opposed to most materials where there is a relationship between the porosity and the mechanical properties, these materials don't have that relationship. Now, the reason why we would like them to not have that relationship is because if you are bound to a specific dependency on the porosity, on the geometry, you don't have enough freedom to design the mechanical behavior and design the fluid flow, which is related to oxygenation, which is related to nutrients, how they transfer. So these two things are coupled. You don't want that coupling. You want them to be decoupled. This is the only known example of a material where you have this decoupling. So this is another example of what would be very important for biomedical implants, and is usually impossible to realize. Now, there are also possibilities. You could have the small scale combined with the larger scale. This is what you see up there. And you could combine them both in the same piece of implant. This is obviously not an implant, but a visualization to show that this is possible. Now let's go one step down, one step further, and to smaller scales, nanopatterns. It's a recent discovery that these little nanopatterns there, they could kill bacteria first. So you could use these nanopatterns to kill bacteria. You could use them to instruct the stem cells to become a specific types of cells. So stem cells, they could become many more types of cells. And with these little guys, which are at the level of nanometer, you could instruct them to become the type of cells that you want. The way it works is through mechanical forces which are applied to the cell, and they regulate certain intercellular pathways, and they cause this kind of behavior. Now, we could make pretty much any nanopattern that we want. This one is made by lithography. Lithography is the same technology that is used in your smartphones. So we could use the same technology to make nanopatterns. We could also make use of a specific 3D printing technology, which is, in this case, electron beam induced deposition, to make anything we want. This nano pattern here, the diameter of this guy is only 10 nanometers. Think about it, 10 nanometers. And you could kill bacteria. This is a bacterium which has been killed. It has been fisted out, the cytoplasm is gone. So you could use these nanopatterns to kill bacteria and to improve bone regeneration. Now, that's not all. You could do more. You could also make 3D printed structures, very complex 3D printed structures at the level of tens of nanometers. It's as small as it gets. There is nothing smaller than this. Now, so that's very nice. We could make anything we want at the level of a few nanometers, but there is a caveat here. And the caveat is that we could only do this on flat surfaces, only and only on flat surfaces. So how do you combine something that is happening on flat surfaces with the 3D printed structures? They have a lot of surface. You would like to be able to combine this technology with this. We can't do that. So what would you do? I asked these questions for years. And the solution I came up with was very simple. If you can't do that in 3D, don't do that in 3D. Start from 2D. So if you can't do that in 3D, start from 2D, which means that you could apply your nanopatterns And then you have to have a self-folding mechanism to fold this into 3D. Now, that sounds very simple, but could you, in theory even, fold a complex 3D shape from a flat state? That was a big question for us and for the rest of the world. And it turns out that you could. We came up with this technology recently. It received a lot of attention from Scientific American, from Science magazine, and it's very simple. Now, when you see it, it's very simple. It took us a lot of time to come up with that. Now, we came up with 3 folding strategies. Depending on the type of unit cell, you could fold these 3D shapes from a flat state like this, or like this, or like this. Now, that's very nice. There is, in theory, a way to fold these complex 3D shapes from a flat state. But can you realize that in practice? Maybe yes. So these are the hands of some of my group members who are holding these. Yes, at least at this scale you could do that. But obviously this scale is way too big for what we want to do, so we need technologies to enable us to do that at a smaller scale. Which is what we came up with, and that was a technology specifically designed for the most inexpensive printers, 3D printers, that you can buy at a toy shop or for a few €100 on the internet, and it uses the most inexpensive 3D printing material, which is polylactic acid or PLA, and it all comes down to the type or the direction of the filaments you put. Now, if you do that, you could do some things, like having self-folding things that you can see here. This is a box, basically. This is a little bit more complex shape, and they could self-fold to the shape that you want them to fold. So when you put these structures in hot water, they go from the flat shape to the programmed shape that you want them to go. But that's not all. What you also would like to have is a sequential shapeshifting, which means that you should be able to program the time of the folding so that they don't collide with each other. So let's see how we have done that.
At the same time, the material on which the patterns are being imprinted is thought to go into a 3D shape when being triggered by an external stimulus, such as heat. Together, this would generate a complex 3D shape with nano patterns.
Our goal was to come up with a method which is fully automated, but also simple and inexpensive.
Using 3D printing, we can program shapeshifting in those polymer materials by simultaneously extrusion and stretching of the filaments. Upon activation at high temperature, the structure will shrink in the direction of printing.
Time delivered work based on incorporating porosity inside the structure of material, which allows to control the heat transfer. And then based on that, we can program the sequence of shape-shifting.
We have come a long way, but we still have a few major challenges ahead of us for the coming years. We should be able to make microscale structures using self-folding techniques in order to be able to make bone scaffolds. The kind of research that we do is high risk, high gain. So I don't know where we will end up 5 years from now. What I do know, though, is that the future medical implants will not look like the current ones. Thank you.
Yes, thank you. Thank you, Amir. This is really inspiring. You also work on the edge of actually many science fields, but now we also see that it's already, there's so many practical applications already. I think we cannot wait. There's time for 1 or 2 short questions. The shorter the question and the answer, the more questions Amir can answer. And after André Kuipers' talk, we will also have more time for questions. So there are 2 catch boxes in the room. Who has a question? There's one question there in the back. Oh, you will get a microphone.
Polylactic acid. Is it also possible with other polymers, or?
Yes, it's possible with a lot of other polymers. Polylactic acid is the most widely available, and it only costs 17 euros per kilo. So that's
So here comes the technical part, where you go from science to application. It's cheap.
Yes.
Great. So if it works with this material, that's perfect. Other questions? Was there one here? Yeah. There's a question there. Is there a catch box on that side? Yeah.
Can you physically make any shape with 3D printing and design software, which automatically folds back a shape and tells the 3D printer how to print it?
You can make a lot of shapes. Not every shape, but a lot of them you can make. And that still is a big question. How could you make any shape? Right now we can do a lot, but not everything.
So the future engineer will solve this problem such that we can make any shape, right?
Perfect.
Okay, because the questions were so short, we can do another question. There in the back. Oh, yeah, there.
Thank you. I have a question about the vertebral body. If you insert your structure into an osteoporotic vertebra, will there be bone stimulation as well, so you get regrowth of bone along the structure?
Yes. So what is happening right now, the procedure right now, is that they put a cement in the fractured vertebral body, but that's not good because there is no bone which is coming back to fill it in. What we have designed here is a porous structures which allows the bone to grow back. So that's exactly what you said. What we hope is that the bone will grow back and you will have the implant with the bone that is ingrown.
And that is unique in the structures that you make, that
Yes.
it helps with the bone growth itself, right?
Exactly. And the unique aspect here is that you bring it there in a small state and make it big. You could also make big things which are going there, but it would be more invasive. So that is the unique aspect.
Great. Well, thanks a lot, Amir Zadpoor. Let's give him a big applause.